Building a functional AI chatbot prototype takes about 10 minutes. We call this Demoware. It is software that performs perfectly in a pristine, isolated environment, but lacks the error handling required to survive a production workload. This visual illustrates the resulting data overload, the chaos that occurs when engineering teams trap themselves in endless tuning loops, attempting to fix system-level fragility by merely rewriting text. The industry currently operates on a false assumption that refining the prompt is the primary engineering hurdle to deploying a reliable product. The math reveals a different reality. Prompt iterations scale linearly, providing rapid diminishing returns and reliability. Eventually, these recursive loops corrupt. Varying outputs produce compounding errors that spread across the execution environment. A product's survival in production depends on software architecture. Prompts are secondary. In local testing, a single isolated user query moves smoothly from an input node, processes through the language model, and returns an output in milliseconds. But testing isolated queries completely masks the variables of network latency and memory state. Introduce load into the system by scaling the requirements to 100 parallel queries, and the environment destabilizes. Inference time balloons exponentially under moderate concurrency, creating sudden, impenetrable latency walls. Consistency breaks down next. Identical prompts probabilistically return entirely different formatting and conflicting answers. Push the simulated system to a true production stress test of 1,000 parallel queries, and the architecture collapses. A single anomalous data format cascades through the pipeline, triggering an edge case explosion that crashes the unprepared execution environment. Without rigid memory boundaries, state context collapses. Data bleeds between entirely separate user sessions. This creates a black box problem. It is impossible to debug a probabilistic engine using traditional linear logging, as identical inputs can generate corrupted outputs with incompatible JSON schemas. Optimizing a prompt is completely useless if the underlying system cannot manage persistent state or handle network latency under load. To force reliability out of an inherently unreliable engine, you must cage the language model within a strict, multi-layered software pipeline. This diagram maps an architecture that forces chaos into structured pathways. Layer 1 is input validation. You must filter out invalid or malicious data before it ever consumes costly compute cycles. These filters act as a rigid security and cost control boundary. Valid data passes through, while the system forcefully rejects malformed inputs. Layer 2 is isolated execution. The prompt executes as a single deterministic shot, preventing unmanaged recursive loops. Layer 3 is deterministic output parsing. Simple text extraction is a fatal flaw. You require strict schema validation to enforce the data shape. By defining these reactions, you preserve the power of deliberate choice, ensuring the application follows your rules instead of the model's predictions. A production-grade system treats the language model as an untrusted third-party component that must be validated at every entry and exit point. The next challenge is memory. Because language model API calls are inherently stateless, the pipeline must manage context. Layer 4 introduces state storage. Relational databases must govern application context. You cannot rely on fragile string concatenation to maintain history. Local state guarantees reproducibility. If a request fails, the system must know exactly what was held in memory at that specific millisecond. Layer 5 is observability. Looking back at the architecture matrix, a single thread must connect every layer to log every action. You must be able to trace the exact chronological chain of events and variables that led to an automated decision. Without this deterministic logging layer, debugging a hallucination at scale leaves no verifiable trail. Integrating full observability and persistent state management transforms a volatile AI feature into standard, reliable software. There is one final architectural vulnerability: the physical location and ownership of your compute and state. We call this execution sovereignty. Relying entirely on external cloud APIs forces your team to surrender control over both latency and privacy. Controlling compute and persisting state locally is the only way to build a highly defensible product. By moving to a local-first infrastructure, you keep all data contained, secure, and deterministic. You replace the brittle dependency of distant servers with the structural integrity of a sovereign stack. Teams that win in this space are not writing better prompts, they are building unshakable pipelines. This interface demonstrates a complete system built on those exact principles. Stop optimizing for the demo, architect for the system. Reliable architecture is where deliberate choice begins.